Today, we're going to dive into a really clever mathematical trick. It's something that powers everything from the calculator in your pocket to super complex economic models. It's a method for solving the unsolvable, and it all boils down to one single elegant idea.
Think about it. You punch some crazy equation into your calculator, and boom, an answer just appears. But have you ever really stopped to wonder how it does that? Especially for equations that don't have a nice, clean solution? Well, it's not magic. It's actually a surprisingly simple process of intelligent guessing.
Okay, take a look at this equation. X plus the natural log of x equals 0. Right off the bat, you can see there's no easy way to get x by itself. You can't just add or subtract or shuffle things around to find the answer. This is where we need to think completely differently.
And here's the big breakthrough. The trick is to stop fighting with the equation. Instead of trying to force a solution head-on, we're going to reframe the problem entirely. We're going to turn it into a hunt for something called a fixed point.
So, what on earth is a fixed point? Well, it's a special number. We'll call it x star, where if you plug it into a function, the function just spits that same exact number right back out. The input equals the output. It's fixed in place. Now, this might sound a little abstract, but trust me, it's the key that unlocks this whole puzzle.
And if you're a visual person, this idea is actually super simple. Picture the graph of your function. Now imagine drawing a perfect diagonal line right through it, the line where y equals x. That exact spot where your function's graph crosses that diagonal line, that's your fixed point. It's the one place where the input and output are exactly the same.
This leads us right to the method itself, fixed point iteration. And it's basically a feedback loop. First, you rearrange your equation so you have x all by itself on one side. Then, you just make a guess to start things off. We'll call it x0. You plug that guess into your function to get a new number, x1. And here's the cool part. You take that new answer and you plug it right back in to get x2. You just keep doing that over and over again, letting each answer become your next guess.
To really see how this works, let's try it on a problem where we already know the answer. Finding the square root of 2. We can write this out as x squared equals 2, and then just rearrange it a bit to fit our fixed point format.
All right, let's start with a really rough guess, like 2.0. Watch this. Our first calculation already gets us down to 1.5. The very next one gets us to 1.416. Do you see how fast we're zeroing in on the answer? In just 4 loops, we've got the square root of 2 accurate to 8 decimal places. So yeah, this method clearly works.
Okay, now that we know this tool works, let's go back to that first tricky equation. But here's where we find a twist in the story. It turns out there's more than one way to rearrange x plus ln x equals 0. And as you're about to see, the way you choose to do it makes all the difference.
We can rearrange it in 2 pretty obvious ways. In approach 1, we could say that x equals the negative natural log of x. Or in approach 2, we could say x equals e raised to the power of negative x. Now, both of these are perfectly valid ways to rewrite the original equation, so they should both work, right?
Not even close. I mean, look at this. On the left, with that first rearrangement, our guesses spiral wildly out of control. They get farther and farther from the answer until they just fly off into chaos. But on the right, with the second rearrangement, the guesses spiral neatly inwards, homing in on the correct solution like a guided missile.
So this is the central mystery, isn't it? We've got one equation, 2 totally valid ways of setting up our little feedback loop, but one gives us a beautiful, perfect answer, and the other one just gives us complete nonsense. What is the hidden difference between them?
The source material offers this fantastic analogy. Think about 2 kids having an argument. If each reply is a little bit calmer than the last one, that's de-escalation. They'll eventually find some common ground, an agreement. But if each response is angrier and louder, that's escalation, and the whole thing spirals into a much bigger problem. Our equations are doing exactly that.
So this idea of escalation versus de-escalation is the key. And mathematically, this behavior is all determined by the steepness, or the slope, of our function right at that intersection point we're trying to find.
And the numbers tell the whole story. The function that went totally chaotic, its slope is about 1.76. It's steep. That's escalation. Any tiny error gets magnified with every step. But our successful function, its slope is about 0.57. It's gentle. That's de-escalation. Any error gets smaller and smaller with each step until it basically disappears.
And this, right here, is the golden rule of fixed point iteration. For the whole thing to work, the absolute value of the function's slope, right at the fixed point, has to be less than 1. That's it. That's the secret. The function needs to be a contraction.
It needs to pull things closer, not push them apart.
Now, this golden rule isn't just a friendly suggestion, it's a mathematical certainty. It's all formalized in something called Banach's fixed-point theorem, and it basically gives us a powerful checklist to know before we even start if our method is guaranteed to work.
So what's on the checklist? Well, first, you need a clearly defined search area. Second, your function can't kick you out of that area. Every new guess has to land somewhere inside. And third, this is the big one. The function has to be a contraction. That's our golden rule, making sure the guesses always get closer together. If you can check all three of those boxes, the theorem guarantees you will find exactly one fixed point. Every single time.
There's a really fantastic way to think about this guarantee. Imagine you've got a perfect, detailed map of the city you're in right now. And you take that map and you lay it on the ground somewhere inside the city. Banach's theorem proves that there is one and only one point on that map that is directly on top of the actual physical spot it represents. A single, unique, guaranteed fixed point.
So, the next time your calculator spits out an answer to some gnarly problem, you'll know the secret. It's not just crunching algebra, it's searching for a point of perfect equilibrium, a fixed point. And this search for stability, it's a fundamental pattern woven into the universe. The real question isn't just how it works, but where else are these invisible spirals of convergence quietly shaping our world?